All right, good morning. I hope you all had a great and refreshing weekend. And so now we are ready to get going on circuits again. So resistive circuits. So that's what we've been talking about. And you've solved a lot of homework problems already. For some of you, probably too many. Yes? There's no quiz today. Why? When is the first quiz? Well, you know, the quizzes are unannounced, but you're absolutely right. There could have been a quiz today. So maybe there is one Wednesday, maybe Friday, maybe next week, who knows? Just know your stuff. So actually today will be a great preparation for a possible or eventual quiz, because today we will actually use the material that we learned about, right? So I just started to say that incidentally, quizzes, if we do them, they will be right at 9:10. So you also have to be here on time in order to get the full 10 minutes or whatever it is to do the quiz. So, okay, but all right, so today there is no quiz, so yes, relax. Hey, you know, I do not want to spoil the weekend either. And it would be also my weekend to create a quiz. Incidentally, though, I did create some sample questions on the web, right? You can look at them. I put a due date that is ridiculously, you know, at the end of September or so. That would be a little bit too late for those questions. So if you have a chance, then go and look at them, and it gives you a very, very good idea of what would be on a quiz, okay, if we actually had it. Right? Any more questions about that? So again, the thing is not to spoil weekends with that or so. I just want to make sure that you're always up to speed with that material, because occasionally I had it in classes that people got very puzzled over voltage dividers. Well, if you get puzzled over that stuff, you really can't follow in class. You really can't think circuits, right? It's like the language that we use here. And you need to be familiar with that. If that puts you off, then the whole class will be painful to follow. Okay, so resistive circuits, we did plenty of them in class, in homeworks and so on, but what can we actually do with them? So here are some interesting things that we could try to build. So you know this famous device, right, or infamous for some people. Anyways, if you hold it, you look at it, you turn it, hey, it figures out. And then the image orients itself right so that you can read it the way you would like it, right? So, hey, you know, it's natural. Of course, it should do that. But did you ever wonder, how does it actually do that? You know, right? Anybody else? Anybody else? Okay, so why don't you tell us?
It's got some sort of resistor that the resistance varies based on what direction.
Okay, that could actually be. All right, so maybe there is a resistor actually inside, and so I actually like that answer, and also that's the point that I'm trying to make here. You know, resistors sound like pretty boring things. Well, not if you if you use them for something that's interesting, right? And so it actually turns out that you can build a lot of very interesting things out of resistors. It turns out that you could build this with a resistor. Actually, inside here is a capacitor that does the same thing, but it could have been done with a resistor too. Okay, so another thing, kitchen scale, and hey, you know, how does it actually work? And obviously, I don't care. I don't think about the designer blue color and so on. Inside, how does it figure out what the weight is that we put on top? Okay, so keyword, we've already gotten it. Let's look at resistors. Could we somehow do this with resistors? So, well, here is a resistor. It's drawn very, very schematically. So a resistor is basically a chunk of material that conducts current, right? And of course, it has a length, it has a cross-section, and then again, there is the material. So first of all, the material, turns out that there are different kinds of materials. Some materials, they are called conductors because, you know, they carry current rather well. And others are called insulators because they really don't want to pass current at all. And supposedly Teflon has a very high resistance. I don't know how to interpret that. Teflon doesn't carry current, right? For all practical purposes, it's an insulator. You could use it as a jacket on a wire, and then if you touch that wire, You touch the jacket of the wire and you do not get electrocuted. There are also interesting materials that are in the middle, semiconductors. And why are they interesting? Well, because there are various ways to affect their resistivity to make them go all the way from being pretty much like an insulator to pretty much like a pretty good conductor, actually. We will not talk a lot about semiconductors just yet. We'll talk a little bit more a little bit later in the course. But anyways, that's kind of a list. So here we are interested in actually conducting current. Right? A resistor should not conduct current too well, but it also should, because otherwise it wouldn't be a resistor anymore, it would be a short circuit, but it should conduct current. So we're picking a material from sort of the upper rows of this list. And then, at the top I showed an equation that relates resistance to a few other parameters. So the first, the parameter L, that's the length of this chunk of material that we use to make the resistor. Well, if you make it longer, the resistance goes up, right? It's the same as a highway constriction, some kind of a building site or so, construction site, right? The longer it gets, the more resistance it puts on traffic. Okay, so that makes perfect sense looking at this equation. Cross-section, well, you know, if you have a highway with 10 lanes instead of just 2, the more cross-section it generates less resistance, more traffic gets through. Makes perfect sense. And then the material just enters as a proportionality constant in this equation. So this equation makes perfect sense. So that's what a resistor is. Now, any ideas on how we could use this to measure a weight? Well, suppose that we had made such a resistor and now we pull on it. We stretch it. What would happen? Well, obviously, if we really pull very hard on it, it's going to break, right? So if you think about an electric wire, copper or so, you can pull a little bit on it, but not really a lot, right? First of all, it's probably strong, and so unless you really work out a lot, you may not be able to break it. But you can stretch it a little bit, right? So if you stretch it, then of course the length goes up. But now if we look at our equation, or the length is in there, well, if we increase the length, the resistance should go up, right? Likewise, when we pull on it, the length gets longer, the cross-section has to get smaller. Why? Well, because the total amount of material, so the total volume, probably stays constant, right? We don't create new material. That would be quite a feat. Okay, so the cross-section actually must get smaller. That further makes that the resistor increases. The material, rho, hey, it's still the same thing that we have there. Consequently, total resistance really should go up. If we pull on it, the resistance should go up. Okay? So that certainly, I mean, this argument, I can't find any flaw with it, right? That certainly must be true. We can, of course, ask ourselves the question, well, how much does it really go up? Is it an amount that is meaningful in any way that we actually could use to make some kind of a measurement? So first thing we do is we sort of start capturing this mathematically. So we say the resistance is really some R0. That's the resistance we get if we don't pull at all, right? That's sort of the nominal resistance. And then we get a delta R, and that's the increase of resistance. And then if we go through some analysis, actually we can find that the percent change in resistance is proportional to the percent change in length. Not too surprising. There is a proportionality factor. Now, it's not too hard, but we won't go and bother with that, to figure that this proportionality factor is roughly 2. Actually, the reason it's roughly 2 is that both L and A change. And that's why we get this factor of 2 other than just 1. So in practice, lo and behold, that has been verified many, many times. That's how the resistors behave. If you pull on it, at least the resistance made appropriately, if you pull on it, the resistance changes with a factor that is about twice the change in length. Okay. Now, of course, as we said already before, we can't pull a whole lot, right? We can't, except unusual materials, so we couldn't stretch them to make them twice as long or something like that. Usually this here is going to be 1% or less. Okay. And that's useful to remember because later we're going to have situations where we compare delta R to R zeros, so well then we can neglect the delta R in some cases. So it's good to remember for later. But in principle, the point is have a resistor, pull on it, resistance goes up. Okay? So actually these things are used all over. They are really useful. They're called strain sensors, or strain gauges. And they have quite many applications. First of all, let's look a little bit how they actually look like, right? So again, a big chunk of metal would be really difficult to pull on. So instead, they're usually made on top of a foil, usually a material called capdem or polyamide. The same thing as flex PC boards are made out of also. And then on top we have traces. They may be copper or aluminum or whatever material, a conducting material, right? And usually manders like that. You're going to use those in the laboratory. In fact, Laboratory 2, you're going to build such a scale, minus the nice designer blue color. And there you're going to use these strain sensors. So if you bend it, then it gets a little bit longer. If you bend it the other way, you push it a little bit together, right? It gets a little bit shorter, and you get the resistance increasing or decreasing, and you can verify that in the laboratory. So now again, how could you use this? Well, hopefully you can use it to build our scale. But we also could, it's also used widely in figuring out deformations in bridges. Recently somebody called me and he said he wanted to equip the Golden Gate Bridge with strain sensors in order to figure out how it flexes. And so, you know, when there was an earthquake, or maybe if there was a really strong earthquake, you would know if it has flexed so much that you cannot pass it anymore, right? So that's one application. So actually, when putting together these slides, I surfed around a little bit on the web for nice pictures. And the pictures that I found are kind of funny. Was somebody found a way to use these strain sensors on mountains to measure how the ice moves around, and from that, don't ask me how, they somehow figure out something about global warming. I went to their website. You can find it here. And there's a whole team, maybe half a dozen people or so working on that, and they all have a picture, and you always see them. They are obviously mountaineers and so on, but they must have taken EE40 and then or the similar class, and then they found the right thing to do, right? That now they have an excuse to do more mountaineering, and hey, you know, it's their work. Sorry, I have to climb around in the mountains. So resistors can be really great if you just have the right sort of mindset and find the right application. Okay, so we are not going to solve or investigate global warming, at least not today with these resistors, but let's focus on this. How could we weigh something? And I'll let you think about how could I build this iPhone orientation sensor or whatnot. So how are we going to do that? Well, there is a schematic drawing already. We have a kitchen table, right, for our kitchen scale. And then on that kitchen scale, we put this contraption consisting of a metal band, and on top of that metal band, we have the resistor. And so this is the strain resistor, the strain gauge that we're going to use. Then very important, you need chocolate chips, so don't forget to bring them along to the lab 2. Huh? And so if you put them here, then, of course, they are going to pile up here. Green chocolate chips. Okay, and then because it gets heavy, well, then this thing is going to start bending down, right? Something like this. I exaggerate a little. Now the top line of the top, this segment here gets a little bit longer, right? And this segment here at the bottom would get a little bit shorter, and the middle line here would stay the same length, right? But anyway, it's the point, and that's kind of mechanical engineer stuff, right? It's not going to be on the quiz or on the test. So I just try to explain you how to use these resistors. So anyways, the strain resistor, which is on top, gets longer, and therefore its resistance is going to go up. And out of that resistance change, we should be able to figure out how many chocolate chips we put there. Okay, so now the fun really starts. Okay, so now we basically know what we want to do, right? Our goal is to build a scale. We know the mechanism we're going to use. We're going to use this strain resistor. And Now, how are we going to do the rest? Well, we have to design now a circuit that takes that resistance and somehow produces an output that then we can display somewhere, right, for example, for our scale. Okay, and so in the middle, of course, we need a circuit, and now we need to design that circuit. And so that's really what EE40 is about. We want to learn how to design circuits. So now circuit design is a little bit of a thing, right? There's a lot of fun stuff, creativity. You can come up with really great circuits, and others have maybe a clumsy circuit or one that doesn't work. It requires intuition. Of course, it requires a bit of work. Yeah, they have to try lots of things, and many don't pan out, and some do. And also, experience really helps. So we're going to do a lot of. We're going to look at a lot of circuits in E40, and if you continue on this, you will look at a lot more circuits in your careers also. Also, it's totally common to go and look at books and publications and so on, look for ideas others had. You got to cite them, but it's okay to copy. You got to cite them, and then it's okay. Anyways, there is one problem with all of these things. I mean, I can make you work very hard. At some point, you complain. It's by experience. You also have some resistance, right? But anyways, and that's okay. Complain if it's too much. Then you get some experience and so on. Creativity, intuition, I don't really know how to teach that stuff. So I will rely on what you have already. But there is some method to it. There is definitely a method on how to go about these problems. There is a procedure that's always again and again similar. So today, for the first time, we go through that for circuit design, through that procedure, and then we will go through it more times. Okay, so we will summarize in the end what we really did, but for now, let's just get going. So the first step really should be something very simple, something that figures out, is it even possible to do that? For example, I have now such a strain resistor, and now notice I went back to sort of a circuit schematic kind of description. Let's figure out whether the resistance really increases, right? After all, this is all a big theory. That sounds great and nice, but does it really work? And so we have the lab instrument, and we can connect it, and we can measure that resistance. We can make the resistor, we can pull on the resistor, right, and see whether the resistance actually goes up. Incidentally, here this shouldn't say volts, this should say ohm, but I didn't want to. Okay, so with that, we really can verify what's going on, and we can verify that indeed there is a resistance change, and so on and so forth. Obviously, that's not a circuit design of any practical interest. You don't want to run around in the kitchen with such instruments, totally aside from the cost. I think it's about $1,000 or so. So what we really want, once we've gone over that first step, and then again in the lab, you're encouraged to do that first step also. Once we verify that things are the way we sort of think them, then we have to figure out what exactly is our goal. How are we going to define success, right, in this project? So on the left-hand side here, we have that strain sensor. Again, that's this resistor, probably on a foil of Kapton. On the right side, probably you're going to use a microcontroller. We're going to talk a little bit about microcontrollers later in class, but they're basically computers. And then with special inputs. So microcontrollers in particular, some of the inputs they have a voltage input. And they can take a voltage, they can convert it to a digital number inside. We'll talk about how that all works. But anyways, they take a voltage and they create a digital number out of it, and then they can display it, or God knows what, calculate something interesting with it or not. So what we really want is that this microcontroller at its input sees a voltage that is proportional to the length change, which, according to equations that we had looked at before, is really also proportional to the change in resistance delta R over R0, and there is some proportionality constant. Okay? So our goal then is to build this thing in the middle here, a circuit that somehow can observe that resistor and change and translate that resistance change into a voltage that follows this equation here. That's what we want to do. Okay? And the microcontroller, right, it can do all sorts of things there. Also getting the weight from delta L over L It's a mechanical engineering problem. You find a mechanical engineer, give him 1 or 2 of your chocolate chip cookies, and then he will tell you how it works. Okay, so we don't need to deal with that. So now we have that thing. We have that resistor. We have that resistor here, the strain resistor, and this is our goal, right? We want to make a voltage, and how do we change that resistance into a voltage? Well, here is the first idea. What is this thing called? A voltage divider, exactly. So now, can you figure out an equation that relates Vx to Rx? I'll give you a minute or two, everybody, so you find your neighbors, shake them a little bit if they're sleeping, and then work it out, appoint somebody who gives me the answer at the end. Take a minute.
Is the current going through Vx?
The current here? Let's make this current here. Huh? The microcontroller only wants the voltage. It somehow miraculously, we'll have to talk how we're going to do that, but miraculously it doesn't pull any current. So what's the voltage given all the other circuit components? Okay, somebody already gave me the answer. So it's Vs times okay, that's what it is, okay? So are we done now? You know, this is correct. But we have to be very, very careful, especially in circuit design. We have to be very, very careful. Equations are not something that we just put 2 bars or a box around it and then we are done. Equations are really things that tell us something about the circuit. So now we have to figure out what this equation actually tells us about the circuit. Remember what we really want. What we really want is a voltage that is proportional to delta R over R0. So now we need to work on the equation that we just derived on the page before. We need to work on that and figure out if we can bring it into that form, the desired form. We have to figure out what K is. And if it doesn't quite go into the right form, well, we need to figure out how is it different and what could we do in our circuit in order to overcome that difference. So that is the first lesson about circuit design. That's very, very important, and that's also important when you're doing your homework. When you're doing your homework, then you sort of get into this thing, well, finally I have that equation, you put a box around it, and you're done with it. Don't do that. Go and figure out what this equation really means, how you can, what it really tells you about the circuit, right? The equation alone is just a bunch of symbols. It's really not very interesting. And so I very often get this feedback that the homework is just busy work. It's not interesting. That's totally true. If you just derive these equations and you throw them away, you just wasted a lot of time. But if you go and look what the equation actually tells you about the circuit operation, you'll find very often some very interesting insight that you will find useful and helpful. Okay, so now we need to go and massage that equation. So first of all, we need to get from this Rx, we need to get to R0 and delta R. So we need to substitute here. So why don't we try to do that? So Vx is equal to Vs times R0 plus delta R over R0 plus delta R plus R ref. Okay, so there is a first thing here. A little bit earlier we said that delta R is kind of small compared to R0. So let's use that in the denominator here, and let's simply get rid of this term here, which makes a small error in our equation. Okay? So this is then approximately equal. So now let me let me factor it. Let me split this up a little. So that's Vs times delta R over R0 plus R ref plus Vs times R0 over R0 plus R ref. Okay? So now, if you look carefully, then you will find that this part of the equation, that's actually what we want. That is really of the form K times delta R over R0. At least if, well, we have to, I guess, choose one more thing. Let's choose R ref. Let's choose that R0. We cannot use R ref. R ref equals to 0, right? If we would make R ref equal to 0, it would look even better. But then, unfortunately, then Vx is always equal to Vs, and we are not measuring anything. So we make R ref equal to R0. Then this whole equation actually becomes Vs over 2 times delta R over R ref plus Vs over 2. Okay? So now what is this? This is really what we want, right? The proportionality factor K in this particular case actually happens to be how much? Yeah, exactly, Vs over 2, right? But then there is another term here. Vs over 2. And what are we going to do about that? First of all, what is that term and sort of what does it mean for our application? It's an undesired term, right? We really didn't want that. It just doesn't fit into that equation. Secondly, what it really means is that we are going to get the right result. We're going to get the voltage that we want. That's the first term, or the first summand in our equation. But then there is this additional one that really shifts the voltage to some other value. Well, now, how could we deal with that? What would be a very simple way to deal with this? Yeah.
Stick an ideal voltage source of half the other source's voltage in the...
Okay. We could use a voltage. All right. That's the first idea. We could use a voltage source to compensate it. An even simpler idea. Well, remember, we stick this into a microcontroller anyways. Then it's just going to be a digital number. That digital number has something added to it that is basically Vs over 2. We have to figure out how to get a voltage into a microcontroller, but let's not worry about that. So now, of course, we could use that microcontroller and tell it, whenever you get the result, you go and subtract this thing. Right? Yes?
So you said that delta R is so small that we can just ignore it, right? So why didn't you do the same thing for the delta R?
Yes, why didn't you do the same thing? The reason I didn't do the same thing is that then, of course, I would have gotten that Vx is constant. So I wanted to get rid of the denominator part here because it makes our equation simple, but I didn't want to get off the other part. It's a little bit sloppy, but I didn't want to spend a lot of time on it. Okay? Yeah. I just choose it, right? Or ref, hey, it's a resistor. I can pick one out of my drawer of whatever value I like it to be. We'll talk more about how we actually are going to implement our ref in just a second. But so getting back to our question, we could, just in the microcontroller, we could subtract that. Why would that be perhaps not such a great idea? Well, the reason it would maybe not be such a great idea, remember that we said that delta R is really a small quantity. Actually, this would be R0 here also, right? So delta R over R is a small quantity. So then this is a small quantity. It's going to be millivolts or so, right, in the lab. And this Vs, well, the supply voltage is 1 volt or 5 volts, whatever, right? So this is going to be relatively large. If we have this change a little bit, what's going to happen? We cannot distinguish it from this. It looks like the weight has changed, right? It really would be bad because any small change here changes that entire thing A small change here really doesn't matter, but then it looks as if this thing has changed, and that makes it that the weight changed. Perhaps you have a cheap kitchen scale, and if you look at it, you set it to it's 0, whatever, and then you go and look at it a little later, and then it's no longer 0, right? Those are effects like these. So we have to be careful. We really need to find a circuit solution. Your colleagues sort of started on one. A circuit solution that allows us to get rid of this term, where we only get this term here, where we don't have this here, because otherwise we're going to make one of these kitchen scales where the 0 drifts all over the place. Okay. So yes, actually there was a good question. Our choice, we want to make our F equal to our 0. How are we going to make two components identical in value? Well, the answer is very, very simple, but it's also as important as it is simple. Of course, we use the same value, right? But the way we do that is we actually physically use the same component. Now, if we need two resistors, that's not so easy to do, but then at least we can go to the drawer and instead of pulling out one resistor, we pull out two resistors. And because they came out of the same factory, done exactly the same way, they're going to be quite similar. Also, if the temperature changes, lo and behold, resistance changes. But if they're made out of the same material, then those changes are going to track also. In fact, my students, they build circuits, and so they do more clever stuff. They often build circuits where I need two elements that are exactly the same. So they pick only one element. One element is always the same as itself, right? And then they build all sorts of circuits around it that switches that element from a first position to a second position of the circuit, and then back and forth, maybe 10 million times a second. Hey, electronics never complains. It just does its thing. As we tell it, we have to tell it right, and then it will do it. And that way we can get two elements behaving exactly the same. So I just mentioned that there are all sorts of tricks that we're not going to talk about in EE40 in any more detail, but I wanted to sort of give you an idea of that, making elements identical. Yes?
Why do you want RF equal R0?
Well, yes, we could also have it a quarter or 2 times R0 or so. And you can look at what benefits you would get if you make it some other ratio instead of just equal. Okay? So you will probably find that making them equal is pretty near a good thing. And then I'm preconditioned, right? I say, oh, gee, they should be somehow related. Well, I make them identical because then it's much easier to make them. It's much easier to make them equal than any other ratio. Right? Okay, so this is how the circuit now is going to look like. Now instead of having just one resistor, we have a second one. And again, if I bend this, then this one gets stretched, and this one gets, and therefore the resistance increases. And this one actually gets squished, and the resistance decreases. All right, so that's how it's going to look mechanically in the laboratory, the setup. It's important. But then afterwards, of course, we have to draw a circuit diagram. And so this is the circuit diagram that I come up with. And now we're going to need two in this idea. And again, this requires some experience. So I thought a little bit about it. And ultimately, I came up with this. So we have these two resistors. We have two voltage sources. And now we're going to look at this voltage here. This voltage here, and I'll let you. We're going to run out of time otherwise, so I'll let you go through the derivation. That's something I'll tell you conceptually how you do that. For example, you could write a KVL loop here, right? So then you have V2, VS2, which is given, of course, that's a source, and Vx, which is what we want to know. You have an equation among those, right? That's that KVL loop. And then, you can write a second equation for Is. Is, that would be equal to Vs1 plus Vs2 over R1 plus R2. Be very careful when you copy these equations. Remember my bet with the $20? Hey, I lost them, okay? So sometimes there is an error in here, so be careful. Don't just copy the equations, rederive them. Okay, so and then once we have IS, we can figure out V2 is equal to IS times R2, okay? And once we have all of this, we can solve for Vx. And we will get Vx is equal to delta R over R times Vs if we choose Vs equals Vs1 equals Vs2. So in other words, these two sources, Vs1 and Vs2, turns out that the good choice is making them equal also. Okay? So basically now we put two batteries into a scale. Okay? So now if we look again at our equation, that's what now comes out of this circuit, right? If I did the analysis right. So Vx equals Vs times delta R over R. Are we done? Yeah, so this is now the correct relationship. The proportionality factor now is Vs. And this offset term is gone. And so in principle we are ready. We could go now to the lab, we could check it all out, make sure that it's really right, and then we could get that hire that designer that makes the nice, beautiful blue case, right? And we could start shipping our scales, producing and shipping. At this point, however, there is still an opportunity. Now there is the circuit designer and there is the great inspired EE40 circuit designer, right? And so very often, hey, there is more than one way to solve a problem, and some solutions are going to be better than others. Now you have a question, I believe.
So the positive side of VS2 is connected to ground, right? Is that like true with VS2? It's like positive side and negative side connected to each other for the second voltage.
Yes, so if, for example, they would be both 3 volts, then you would have, if we make this ground, then you have plus 3 volts up here, and you will have minus 3 volts down here. Right? And the total voltage across here would be 6 volts.
But if the positive side of VS2 is connected to ground,
Mm-hmm.
so doesn't that mean that like its negative source and positive source are connected to each other like through wire? Because like
These are 2 batteries, right? If you take 2 batteries, then they're not intrinsically connected, right? What literally, let me try to understand what. So let's say I physically could take 2 batteries, right? Like this. If they're lithium batteries, then the voltage across here would be 3 volts, and across here it would be also 3 volts, right? Now I can put my ground anywhere I like, right? If I put my ground, for example, here, then I just arbitrarily say, I want to call this 0 volts. Okay? And now, of course, if I go and use my voltmeter, I find out that this voltage here, lo and behold, is 3 volts. And this voltage here is also 3 volts. Well, but now, here we have 0 volts, and then we have to subtract 3 volts, so then here I get minus 3 volts. Okay? Make sense? All right. So, can do that. Good question. That's the kind of stuff that I remember I had that also. I looked at stuff like that and made no sense to me. And often I wasn't very bashful. I wouldn't, just like you did, I would interrupt the professor and would ask the question and say, And then I soon found out, because my colleague said, how do you dare asking these questions? And I found out that everybody else had exactly the same question, but didn't bother asking. So they were thanking me that I asked. Well, so thank you that you did ask, right? Okay, great, yes. And so join him, ask questions. It's the only way that we get over this. Some things seem obvious to me, but, get over it first. So anyway, so the problem here is that we need two batteries. And it also turns out that if these two batteries actually were not exactly the same value, if you go through the math, and so you'll find out, then you get again one of these offsets. And so that is kind of inconvenient because, if people, like your kitchen scale doesn't work anymore, oh, it needs a new battery, so then you pull out two batteries out of the drawer, but some people are not careful. They use one fresh battery and an old one, and then the kitchen scale has an offset, right, and doesn't work right. You don't want that. So ideally, we have only one battery, and then it's always the same as itself, right? So okay, so here is a slightly improved circuit now, where we actually have 4 of these resistors. How are we going to do that? I should have a slide here, but I don't, so let me just go and try to mock up. Okay, so instead of having just one resistor on top and one resistor at the bottom, we can have 2 resistors on top and 2 resistors at the bottom. In practice, I probably would put one in front here and the one behind it, because here maybe the metal bend's a little bit different than here, and therefore the delta will be a little bit different, but I can't draw it that way. So probably in practice, I would have one here and then one just in front of it, okay? So now I have these 2 resistors both increase when I increase the weight here and bend this thing, and these 2A and B, they actually decrease. All right? And out of that, I can build the circuit that I showed here. So that's now a fully balanced circuit. It's actually called a full bridge circuit, whatever its name, right? And it has these 4 resistors, 2 increase and the other 2 decrease. And again, we can do a bunch of math to figure out what Vx is. In fact, it's quite simple. It's quite simple. How would we find out the voltage Va? How could you find out what Va is? Yeah.
It's just V by 2. Isn't it?
It's what?
It's just voltage drops across R2.
Yeah, exactly. So the circuit would be voltage divider, right? We really can treat R1 and R2 as a voltage divider. They divide voltage Vs, and so Va, if we, let's say, call this ground, then Va, which would be this voltage, right? Va would be equal to Vs times R2 over R1 plus R2, okay? Likewise, we can do the same trick here to get Vb, and then we have Vx is equal to Va minus Vb. Okay? And so I think actually there should be a minus sign here, but whatever. In principle, this equation is correct. Aside from the sign, maybe I believe it's correct. So voltage Vx is now Vs times delta R over R, and we need only one supply. Okay, and so therefore there is not going to be a mismatch, and it's a little bit simpler and so on. Okay, so that's what we're going to build, and again in the lab you're going to build this. Later we're going to add a microcontroller, a display, can have touch sensors and so on, so that you don't destroy the buttons when you have chocolate on your fingers. We'll get all of this stuff, right? Yeah, it's got to be practical, right? And there must be a reward, right, if we design circuits. So why not chocolate chips? Okay, so we have a few more minutes to summarize what we actually did, right? So we started with something very simple and admittedly impractical, but at least that told us that we are on the right path, right? Lo and behold, these resistors actually do change when we change the weight, right? We figured that out, and it's actually working. It's very important that we do that, because every once in a while it happens that somebody goes to the lab and you make an assumption, right? The resistor changes, but something's broken, it doesn't actually even happen. And we spent hours and hours and hours debugging until we find out that we forgot to connect the power supply or something stupid like that. So one thing, when my circuit doesn't work, and even if it does work, the first thing I usually do in the lab is I take my voltmeter, and I know on this component here I should have the supply voltage 5 volts. I check, do I really have 5 volts there? And 99% of all the time, I just wasted my time, right? Because, of course, I've built my circuit that I have the supply there, and lo and behold, it is there. But in that 1%, when it's not there, I save myself hours and my last few remaining hair fixing that problem before coming up with the most unbelievable explanation of what's going on. So first try, make sure that you're sort of on the right path. Then the second thing is also very, very important. When we design something, we better know exactly what we actually want. Of course, that sometimes evolves over time, right? We get smarter and find out new great ideas, what we can add also. But we need to know what we do. Very important thing, if ever you're going to do a PhD, that's the most important thing. And actually, we have a special exam called qualifying exam, just about that, because some student, PhD is very open-ended research, you can do anything. Well, that's true, but you still better have a plan. You better know where you want to go, right? Otherwise, you're wandering in circles. Okay, so figure out what you really want. Very important. And then once we know, then we can start with a better idea that maybe already is almost practical. It can still have some warts and so on that we will have to address later. Then we go and analyze and figure out what's really not quite right and where we don't meet our goal. We come up with ideas on how to make it better. And this is very, very simple. But, this stupid, trivial recipe, you got to use it. And often in the heat, it's this tree and forest and so on. We forget that, and then we start doing senseless things, and we spend a lot of time, especially at night, not actually getting anywhere. Okay, then figure out how to make it better. Then we repeat, of course. It's an iterative process until we come up with something that we're now really happy with. And then we go and build it in the lab and check it out and ultimately, get rich and whatnot. Okay, so that's how design works. So that's that method that I told you about. The creativity and so on, you really need to deal with it, but the method, that's how we do that. Well, electronic sensors, that's sort of what we built. And hey, there is a lot of things that we can do here, right? There are lots of different sensors. Turns out even just resistors, there are ones that are sensitive to strain. We just looked at them. Light, there are other ones that are sensitive to light. In fact, Lab 3 is you're going to build one of these things where you walk through the bell rings or something like that, right? There are ones that sense temperature, you can with microphones and so on and so forth, right? And then you build this electronic circuit. So that's EE40, right? You build the electronic circuit, ultimately go into a microcontroller, and we'll talk a little bit about those also later on. And here are a few samples of these sensors. In particular, you will read sometimes about something called smart sensor. What a smart sensor, it's probably not really smart in the sense that we hopefully are smart, right? But the idea is that it takes something as a concept like that, and then it adds electronics around it to really take care of all the things, like if it's nonlinear, it takes care of that. It has an offset, it takes care of that. If it's whatnot. So this is one of these sensors, a 3-axis accelerometer that we built in my group, and so there is lots of electronics around it that goes and figures out what's really going inside, and it actually produces already a digital output ready for the microcontroller to work with. So that's design, and then again, as I said, you need to, of course, add imagination to this. So there's something else that I found when looking at the web. Do you know what this is on top? Well, it's the pole of a ski lift. And somebody instrumented this in order to figure out when it would fail. And lo and behold, he got to go to Colorado and probably needs to ski, right? And so why not? You figure out something, equipping skis with strain sensors, if you like skiing. If you like surfing, you will find something else, right? And add strain sensors to them, get a sponsor, and you will produce interesting research paper and get a little bit of skiing in on the side. Okay, so I always try to tell you what I really expect you to carry away from this. Of course, I hope that you carry away really a lot from this one lecture here. But the sort of really the imagination, creativity, that's not on the test. I don't know how to teach it, so I'm not going to test it either. But I encourage that you use it, right? That's really the part that makes 4D being something useful as opposed to just, hey, it's yet another requirement. So in 40, we learn basically the plumbing, right? And so you have plenty of homework where you apply KCL, KVL, dividers, Ohm's law, and so on, and how to use them. That's going to be on the test and so on. It's not really what 40 is about, but that's the part that I can exactly teach you, that it's precisely formulated, it can have an equation, and I can test it, right? But that's not really what 40 is about. We will have a few examples how we use them in a creative way in the homework, in the lecture, and then also a few design examples in the lab. Okay? See you Wednesday.